warm-up. We are recording. Let me get the slideshow set up. Before we get going, let me do one more thing, and that is update you on a few minor or not so minor items. Okay. First, I've missed the last 2 Fridays on campus because I've had an infusion 1 and meetings the 2nd. Okay. Had no time to get, I got some things done while I was in line waiting, for the labs, waiting for the infusion. I got some things done that first Friday. I got nothing done the second Friday. Well, not quite nothing. I got to Birmingham campus a little early and sat in the car and graded a few papers. But that's all I got done last Friday. And then this was a very busy weekend. I got very little done. I got a few more papers graded, but I got nothing put in Blackboard, which I always like to do that on Fridays. And I got nothing done on your attendance. I had done some things earlier, so it could be possibly a little bit up to date, but not completely up to date. So, if you happen to notice that nothing new has been put on Blackboard or on your attendance, that's the reason. Now, with that in mind, I do have, at least I hope to have, 2 hours of office hours this afternoon, 3:15 to 5:15, and I hope to get some of that stuff caught up then. When I say hope to, in between the last class and this class, I had 2 applications for graduation. I had 15 minutes, okay? 2 applications for graduation. The first student had everything in order, got that done fairly quickly. The second student didn't have the degree plan, so I had to send him off. So he's coming back sometime or another. I know I'll be working with his, and then it's like Nicole just went down to get hers. So no guarantee I'll be able to do office hour stuff during my office hours. I might be doing student stuff, which is what office hours are for also. But I'll try to get some of that caught up today. Okay? If not, I have a little bit of time tomorrow, but it'll probably be Wednesday before I have another 2-hour period to do it. But how about next Friday? Well, I'd rather get it done before next Friday, but unfortunately, with next Friday, I have my annual physical at 8 o'clock in the morning, which I'll be at the clinic before 7:45, so I won't be on campus when I'm usually there. But the good news here is, at least I hope it is, usually the physical hopefully won't take more than an hour. So that means hopefully I'll be able to leave the clinic and head to the Birmingham campus, hopefully to get there before 9:45 or 10 o'clock, sometime in that time frame. However, the last time I had a physical, I happened also to have my flu shot that same time, and the nurse who gave me the flu shot happened to stick herself with the needle before she put it away when she was trying to dispose of it. So therefore, it had nothing to do with me except she had given me the shot. So I had to go and get blood work done so they could make sure she didn't get any contamination from me. Of course, I couldn't have gotten any from her because she did it after she gave the shot. So I had to, and that wasn't scheduled, so I had to sit and wait. So sometimes things happen at clinics that are untimely, okay? And I can't guarantee I'll be back on campus by 9:45 or 10 o'clock, but I'm going to do my best to get back by then. Okay, so anyway, I hope to be able to be back on schedule sometime after my physical is over on Friday. All right, done. Next, any questions for anything we've covered so far? All right. Where we left off last time was this theorem number 5, which was the number E, and they were going to take you through parts of the proof. Okay? Now, I think I already read to you the little side note they have here. The E is a little bit complicated in that it's an irrational number. This is on page 127, section 3.2. And in your book, it's somewhere else. Okay. It's so bizarre. It is in your book, so it is a transcendental function. So why didn't they put it where they did in the others? I don't know. Yeah. But they still did it. They just moved it somewhere else. Okay. And as they go about doing this proof, they're going to not start with E. Okay, well, I was going to say they say in the side note, e is complicated in that it's an irrational number. It doesn't have an exact decimal representation. It can't be expressed as a rational number, as a ratio of two integers. So in that sense, it's a little complicated. But on the other hand, as you saw from the previous theorem, that the derivative of e to the x is e to the x. Now, how can you get any simpler than that? So the fact that that's true, they call e the base for the natural number system, or the natural base for our number system, from a calculus viewpoint. Which means also later when you get to integration, the integral of e to the x is e to the x, okay? So it's just the perfect little function to either take a derivative of or an integration of, because it doesn't change when you do either one. So that's what makes it a simpler function than basically any other function. So how they go about to prove this, and they're going to lead up to this formula here. I won't jump there yet. Here's how they go about proving it. Starting rather than e, they're going to start with the function. Let me get my pen set. Okay. Start with the function f of x equal b to the x. Okay. Now, what are the requirements for b? B just has to be greater than 0. We don't want b being negative, and we don't want b being 0. If b was 0, we know the answer. That's a constant 0 function, not very interesting. Okay, if b were negative, oh boy, what a pain in the neck that would be. Anytime x was an even number, an even whole number, it would be undefined. And otherwise, it would be very difficult to define. So we won't go there either. Okay, so we'll keep b positive. It doesn't have to be a whole number. It just has to be a non-negative real number. Okay. Now, it says we'll take for granted a few plausible facts whose proofs are somewhat technical that we're not going to do. And the first, we're going to say that function there is differentiable for all b greater than 0. Okay? Now, if that's the case, that it is differentiable, then what would be the derivative? F prime of x would then be our good old limit formula. Limit as x approaches, as h approaches 0. Let me make sure that's the one they're going to use. I was thinking they're going to say x approaches a, but I thought, nah, they're probably going to do h approaches 0. And I was right. Okay, h approaches 0 of f of x plus h minus f of x over h. Now, obviously, in that form, it's undefined as h is approaching 0, undefined at 0. But let's see if there's anything we can do to simplify. Well, first we've got to do f of x plus h. Now I'm going to leave off the limit part just because I don't like writing it every time. I'll bring it back in when it's important, necessary. Okay, b to the x plus h minus b to the x over h. Okay? Well, what do we mean by b to the x plus h? Rules for exponents tell us this is b to the x times b to the h minus b to the x, that's a b to the x, over h. Remember, if you have same base, different exponents, multiplying them together, keep the base, add the exponents. Okay, so that's good. Well, now we can factor out a b to the x. And what we're left is a b to the h over h. Okay? Well, now the minus 1, sorry. Okay, because factor out a b to the x out of there. You have b to the h for the first part, minus 1 for the second part over h. So that's why they jump down here and say, and let's put our limit back in here as h approaches 0. Okay? So that gives us this line right here. I'll blow it up. That's how we got there. Oh, wait. One thing. Oops. One thing else before we got there. Sorry. You got the b to the x here. That has no h dependence at all. That's just a number. Pull it outside. The limit as h approaches 0 only affects the parts that have h in it. So the b to the x is out front. Now we're just looking at this part here. That's what they're looking at here. And they're calling this some other function m as a function of b alone. Okay? And this is going to be multiplied by our b to the x. Okay? Now, I guess they do this, and I guess there's a reason for them doing this, but I would like to use m, because I think of m as being a slope function. And this isn't necessarily talking about a slope. It may turn out being that. I mean, the first derivative is a slope, so maybe that's why they're doing it, but I sort of wish they'd have done something a little more removed from other symbols we use, and then say, oh, look at this. This is a slope. Let's go back and call it m. I hate for them to do it now. It sort of gets you thinking it's going to be a slope, and it may be. But let's take a look at this. We know the denominator you can't do, but what's b to the 0? 1 minus 5. So you do have an indeterminate form, 0 over 0. This still has hope yet. Okay. Now, so let's go back to what we had before. What this will then be is b to the x times the limit. Well, wait. Okay. I should maybe write this. Limit as h approaches 0 of b to the h minus 1 over h, which is an indeterminate form. We just redefined this as b to the x times m of b, some function of b, if that limit exists, and we're assuming it does, so that's what we're down to now. Okay? Did they help you?
Yeah, since it's a finding my horizon, they said that you possibly could do this.
Okay. I can, but I don't want to do it right here.
Oh, yeah, that's
right. Okay, but I will also need, yeah, that's a copy of your degree plan. Okay, I mean, you can do it after class too if you want to. You don't have to do that now, but unless you don't, I'm going to have time after class. You want? Okay, well, you can go get it now. That'll be fine. Yeah, right. Okay. There goes lunch hour. Okay. Okay. Sorry, I shouldn't think in those terms, but I did. Okay. So whatever this limit is, and we're going to assume it does exist because we're going to do this. So basically, what this is saying is that the derivative, which is where we started, this thing is proportional to b to the x. And that's the constant or variable of the proportionality. Okay? That's what they're getting at here. So it says that what we've shown here, the derivative of f of x is equal to b to the, what we have shown then is that the derivative of f of x equal b to the x, yeah, is proportional to b to the x. That's what I just said. Now that's not a constant proportionality, it's a variable proportionality. So I'm not really all that comfortable with the word, with the term. But basically they're saying that if you go back here, this is d by b to the x dx is equal to that. Okay? which is basically what this says, okay? So I wrote it, but they've gotten it written here too, so since theirs is probably a little more readable than mine. There it is. Now, it says, before continuing, let's investigate M of B numerically using equation 7, which was the one we had, whoops, this one, okay? They said, let's investigate that numerically. And they give you 4 numbers to investigate it for, okay? Now, I'm not going to do all these, but I'm going to put the results here. Oh, boy. I think here is where, again, we hit a break between what the slide set is doing and what our book is doing. So let's do what our book is doing. Let's just make sure it's not going to show up. No, here it is. Sorry, I went the wrong direction. Here it is. Sorry, it's here. Whew. I thought I got to write that table. Thank you for not having to do that. Okay, so that is on the same page here. All right, so what we're doing here, we're looking when H is equal to 2, B is equal to 2, B is equal to 2.5, B is equal to 3, and B is equal to 10. Okay? 3 close together and 1 way out there. Okay? And let's do H's close to 0 and get closer and closer to 0. They're going to start with 0.01. So if you do 2 to the 0.01 minus 1 divided by 0.01, they say you get this. Then do 2 to the 0.001 minus 1 divided by 0.001, you get that. Okay? 0.69 doesn't change, but you go from a 5 to the 3 for the third decimal. Let's go to 0.0001, 2 to the 0.0001 minus 1. That's going to be a very small number, divided by a very small number. Now you get 0.693 with the fourth digit having a change. Okay? And now we have Rodney here. Okay? Just missing Samaria. She wasn't here Wednesday either. I hope she's okay. Okay? And then we go 0.00001, very close to 0, 2 to the very close to 0, so it'll be very close to 1. The difference in the numerator divided by the small difference in the denominator is still 0.6931. Go to the fourth decimal place off on the fifth. So they say it's about 0.69. About 0.69. I would say it's about 0.6931. I think you can, or maybe 3.2, or maybe 3.1. 0.693 for sure. I would put an extra digit in there. It doesn't look like that's changing. That's your M of 2. Now, again, don't think of that as a slope yet. Think of it as just a function of 2. Now we're going to plug in 2.5 and you go through the same 4 values. And you see you start out with a 0.92, 0.9167, 0.9163, 0.91629. Boy, that looks awfully close to 0.916. They say 0.92. I would say you can go better than that 0.916. So, well, let's go to your B equal to 3. Okay? For B equal 2, it was this. B equal 2.5, it was that. And B equal 3. 3 to the 0.01 is 1.10, blah, blah, blah. To the 0.001 is 1.099. To the 0.1098, 0.0986. So this looks like it's probably good to 4 digits here, 1.0986. They say 1.10, which is very conservative there. And when you jump up to 10, way up there, it goes up to 2.3, blah, 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 blah. Okay. Again, I would say 2.30 is probably good as you can do right off the bat, because that next digit, even though it's a 2 for these two, it looks like this is going down. It might get See, I would draw that to, what, 2.303, but if it keeps decreasing, it could go down to 2.302. I don't know if it's going to get there or not, so 2.30 is fine. Okay. What was their point here? Why would they do this? Because remember what we're doing is, and I'm going to lose the screen when I do this, we were saying that f prime of x is equal to, when f of x is equal to b to the x, f prime of x was b to the x times one of these functions. And when this function is less than 2, or down around 2, this is 0.69. When it's around 2.5, it's 0.92. When it's 3, it's 1.10. When it's 10, it's 2.3. So it's changing, but not changing much. So the point of interest here is somewhere in between 2.5 and, ding, 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 perfect attendance. Way to go, team. Way to go. Okay? Some areas here. Okay. The point here is that somewhere in between 2.5 and 3, you got a place where this was 1. Exactly 1. So then at that point, the derivative of b to the x was b to the x. Now it's not anywhere else, but it is there. Now, I'm going to have you do something else. I'm going to have you get your calculator, okay? And let's see. I want you to plug in a few numbers for me. It's not fair. I can't quite get you to do that yet. But just for fun, do it anyway. Okay. Find the key that's the LN key. Okay? Do the log of 2. LN2. You done it yet? Say again? Woo, look at that. Okay? Do the log LN of 2.5. For what? Let's do the log of 10, or 3. Log of 3. Ln of 3. Anybody? One. Whoa, look at that. Do the Ln of 10. Look at that. We're up to 2 points. Yeah. 3 decimal places, you got it. So look at this. These are constants. Okay? For every number you put in there, there is a limit for that part. And that is what you're multiplying by b to the x. And that number you happen to be doing is the ln of b, the log of b, natural log of b, which we haven't talked about yet. But notice what happens somewhere in here, somewhere between 2.5 and 3, you're going to get that constant to be exactly 1. And here's the contention. When that number between 2.5 and 3 is exactly that number E, right? Then the limit of that is 1, so f prime of e to the x is e to the x without something multiplied or divided by. Okay? So sure enough, that's how they go about contending that. Now, you'll also see E expressed this way. Let me go back to here. You'll also see E expressed as EXP of X. That way they don't superscript it, they just put EXP. That function EXP is the same as E to the, okay. Whenever we refer to exponential function without specifying the base, the reference to it is to f of x equal e to the x. The number e has been computed to an accuracy of more than 100 billion digits. Okay? They say calculate it to the nearest 20 places, and, well, they don't say, but to the nearest 20 places, it's 2.71. Notice that's in between 2.5 and 3. 2.71, 82, 81, 82, 84, 59, 04, 523, 536, and it keeps on going, never repeating a pattern. It's not quite as familiar to us as pi, but pi is the same way. 3.14159, blah, 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 never repeating a pattern. Same thing for E, okay? That's the number E. And they've taken it to 100 billion digits, and it never repeats. Totally irrational number. Okay. So, using an infinite series, and they'll do this in exercise exercise 93 in section 10.7, which is way in the future, we can show that E is irrational, and we can compute its value to the desired number of accuracy. They took it to 100 billion. We won't do that today. And for most purposes, the approximation 2.7, they say 2.718 is adequate. I am happy with 2.7. Okay, it's not going to be precise, but it's going to give you a pretty good guess. Okay? Now, the next thing they do here is a graphical interpretation. All right. The graph of f of x equal b to the x passes through every one of these points, no matter what value b is. No matter what value b is. B to the 0 is 1. Any number to the 0th power is 1. Remember, b can't be 0. It can't be negative. It's only positive values, and as long as that's the case, because 0 to the 0 is not defined, okay? But b to the 0 for all positive powers of b is exactly 1 at x equals 0. Now, the tangent lines to these slopes, here is 2 to the x here, here's 2.5 to the x there, there was e to the x there, and there was 3 e b to the 3x there. Okay? So in every case, the tangent line is getting slightly steeper as b increases. So maybe that's why they called it m of x. Okay? That it had something to do with slope of tangent lines. Now, these are all at one single point. You could do this for any other point, but you see none of the other points are going to have the same value at the same place. Okay? There they do. Okay? Now, what they got from these two, and this is why I had you do it, now they're telling you. Of course, it's going to shrink again. Here is the conclusion there. D by dx of b to the x is equal to b to the x. Remember, we factored that out, and those things that Samaria was calculating for me turned out to be log b. Okay? So it's going to be proportional to b to the x, and that constant proportionality is going to be the log of whatever that base was. Now remember, originally, we're letting that only be positive numbers. Okay? Doesn't have to be a decimal, an integral. It could be a decimal or a fraction, rational or irrational, whatever. So let's do example 8. I think this is the graph we're going to use. Find the tangent line to the graph of the function f of x is equal to 3e to the x minus 5x squared at x equal 2. Okay? So what we want to do is find the tangent line. Now, what are we going to use to get a tangent line? What do we need? Before you can give me an equation of a tangent line, what do you need? Okay, you'll certainly need a y value, and they gave you when x is equal to 2, so we can find out what f of 2 is. What is f of 2? From this formula here, 3e squared minus 5 times 2 squared, right? Which would be 3e squared minus 5 times 4, so that would be 3e squared minus 20. Okay? Now, that's not a very convenient number, but it is a number. An irrational number, but it is a number. Okay? So you're right, we do kind of need to know that. Okay? Not right away, maybe, but we do need to know it. So what we have now is an ordered pair. 2e to the 3 squared minus 20. Okay? Strange number, but there. Okay? Now what that gives you is the point where x equal to, the y is equal to this value. Now, let's do it. Someone plug this in. 3e squared minus 20. .1 something or another. So sure enough, that point is just above 2. Okay? Got it. Okay? Oh yeah, they have 2.17. Is that what you said? Yeah. Okay. And they also have that the slope is 2.17. Now, we haven't gotten there yet, but we're going to. Okay? Okay. No, yeah, wait a minute. Boy, there's too many 2.17s on the board right now. Is that what you said? 3e squared minus 20 was?
It's 2.167.
Wow. This is bizarre, but it's true. When x equal 2, that's the y value. It's also going to be the slope. It's also going to be the opposite of the y-intercept, because the y-intercept is going to be negative 2.17. This is totally strange that you have that same number in so many places in the same problem. Okay. Yuck. That caught me by surprise here. Okay. It's there, but it's not for the reason you expect it's there. I'll just leave it like that. Okay. That's f of 2. Okay. So you got the xy point on that thing, and it just happens to be this ordered pair right here, 2, 2.1. I'm going to round it to 2.17, which is bizarre. I'm going to put this as approximately because it's not exact. Okay? Now, you did need that, but not for the reason I was expecting. Not the same reason it's showing up on the graph in two places there. Okay. So we first calculated f of 2. There we did it. Now that's going to be useful in the calculation of a tangent line. But we're not there yet. What else do we need to get the tangent line? The equation of a tangent line. Give me some equations of line, standard equations of line. Y is equal to mx plus b. Now that would be fantastic to know if you knew what the slope was and the y-intercept. We don't know what the y-intercept is, okay? So that's not particularly helpful for you here. Can you give me another one, a little more complicated? That's the simplest. That's the one I always like to go to, and that's the one they're using here, but we don't have enough information to get there yet. But what it does suggest to us, what's the other thing we need? We need to know what f of 2 is. We just calculated. That's 2.17 approximately. The what? The derivative. Very good. We need to know what the derivative is. So if this is your function, f of x is equal to 3e to the x minus 5x squared. What would be f prime of x? No, not natural log. 3e to the x. Remember, the derivative of e to the x is e to the x. Makes it so easy to use. But the next part, we got something else. Minus 10x. Okay? So that's the derivative of f at any place on that. You know, any x value, plug it in, you can get the derivative. We're interested where? At x equal 2. So f prime of 2, and what is that going to give you? The slope of the tangent line at x equal 2, right? So f prime of 2 would be 3e squared minus 20. And guess what? That's exactly what f of 2 is, isn't it? That is also f prime of 2. And that was also about 2.17. Duh, where is all this coming from? Okay? Now, if you know the slope and a point, if we knew the y-intercept, we'd be happy. We don't know the y-intercept. But we do know a point that's on that line that this is the slope of the line is this, which is about 2.17. Okay, so we got the slope, but we also got the point. When x equal 2, the y is equal to 2.17, right? Okay, now, if you know the slope at a point, can you give me an equation for that one? Point slope formula, exactly. How does that go? Okay, I'm going to jump back half a step. If you were looking for the slope at 2 points, what would be that formula? Okay, m is equal to, okay, no, y2 minus y1, right, over x2 minus x1, right. Rise over run. right? Now, what I'm going to do next is multiply this by both sides, by the denominator by both sides. Multiply by x2 minus x1. Okay, here they go out. I'm going to rearrange the order into y2 minus y1 is equal to m times x2 minus x1. Is that looking familiar now? Now what we do now is, okay, this formula here was if you had 2 points and you're looking for the slope. Rearrange that you have 1 point and the slope, you're looking for the equation. So basically what you do, you lose the subscript here. And that gives you the point slope formula. Y minus y1 is equal to m times x minus x1. Where your point is x1, y1, your slope is m, and this will give you an equation of the line. So let's do that. Y minus, and what's your y1? 2.17 is equal to m. What was your m? 2.17. Driving me nuts. Times x. X minus 2. Got it. Okay? Now, let's multiply through. Y minus 2.17 is equal to 2.17x minus 4.34. Right? And what's one more step to get it to a form that looks like that? Add 2.17 to both sides. And that gives you y is equal to, huh?
Oh, sorry, whenever you add it and
right.
To the other side, sorry.
So y is equal to 2.17x minus 2.17. Are you getting sick and tired of 2.17? That's exactly how they got this formula. Now, quick review. There's your function. Okay? If you're looking for a tangent line at a point, you need to know the value of that point. They give you x equal, you figure out what the y is. Okay? Then, you need the slope at that point. So you take your derivative of f of x. Once you get that, then plug in the point. X equal 2. Okay? The x value of it. And you get that. Okay? And then, you know that y minus y1 is equal to m times x minus x1. You plug in the y1 from your point, the m from your slope, and the x1 from the point, and then you solve that and get it into slope-intercept form. And this one, everything's a 2.17, which is really a bit bizarre. Okay? I wish they had given you something. You can't expect that always to be the case. Sorry. Here comes. All right. So we've done example 8. They show you another conceptual insight here. And by the way, if you drew this line, here you see that indeed it is tangent at that point there. If you go back just a little way here, that would have been 0. So certainly, you can't say that these things are always going to have that same value showing up in every configuration. It's not. It's just they happen to pick one that was. Okay? Now, your next conceptual insight here is what precisely do we mean by b to the x? We have taken for granted that b to the x is meaningful for all real numbers x, but we never specified how b to the x is defined when x is irrational. If n is a whole number, we know what b to the n is. Okay? It's simply the product of b times b times b times b times b for n times. For any rational number, x is equal to m over n, then your b to the x would be b to the 1 over n times raised to the nth power, or the nth root of b raised to the nth power. But when x is irrational, you can't express it as a ratio, that variable as a ratio of two integers. That definition doesn't apply, and b to the x cannot be defined directly in terms of roots and powers of x. However, it makes sense to view e to the m over n as an approximation to b to the x when m over n is a rational number close to x. Sorry, I'm getting a lot of drainage. I don't know why. I'm wishing now I had taken the chance to go down to my office and get something to drink before classes started, but I was running around. And by the way, not all of you were in here at the time. I'm guessing none of you are taking a biology course this term, are you? Or are you? Okay. No. Because the two biology labs right down the hall here are both locked up with biohazard signs on the door. And I can only guess that means they had a spill or something over the weekend.
They're experimenting. We know the real story. You don't have to come for them. We know that they're conducting some secret, top secret experiments in there, and they're actually designing something. We know.
Yeah, but why'd they let you out?
I know.
No, never mind.
How do you know? All these government agents come in. Get them. You know.
No, I was suggesting you might be the expert.
Yeah,
No, I'm just kidding. Okay. Never mind. Okay. All right. What they're saying is pick a ratio that's close to your irrational number. Okay? If that irrational number is 3 to the square root of 2, okay? 3 to the square root of 2. We don't have a definition for an exponent that'll give us any help there. But if we express that, someone tell me what the square root of 2 is.
What is that? 1 over... sorry.
1.414 approximately, isn't it? How about let's just use 1.4. So why don't we say that, and that is exactly 14 over 10, which is exactly 7 over 5. So why don't we use that? So we'll say 3 to this is going to be approximately equal to 3 to the 7/5, okay? Which would be equal to the 5th root of 3 raised to the 7th power, okay? And then you could come up with an approximation, okay? And if you wanted one better, do 1.41, which would be 141 divided by 100, okay? And do that one. Or 1.414, which would be 1.414 divided by 1,414 divided by 1,000. You can keep getting ratios closer and closer to what this is, even though you'll never get there. But then the limit, as you keep rounding off there, you're going to get numbers closer and closer to the slope of that line. Secant lines jump at a discontinuity. Why that's put in here, I don't know. We don't have a discontinuity here, but I guess you could approach one thing from the left and another from the right, and then as you get closer and closer, they get closer and closer together. Okay. They say, see exercise 80 and 5.7. That's 2 chapters away. Lots of water under the bridge. Why are they going over it now? But they're saying you can do that kind of stuff. They're getting you ready for the future. Okay? But sure enough, as you let that ratio get closer and closer to reality here, that's getting closer and closer to the actual slope of the number of the value. Okay. Now, the next subtopic here in 3.2, differentiability, continuity, and local linearity. Okay? Hopefully you kind of run into the first two terms or something like them earlier, but maybe not local linearity. In the rest of this section, we'll examine the concept of differentiability, okay, more closely. We begin by proving a differentiable function is necessarily continuous, okay? Now, in particular, a differentiable function cannot have any jumps. And that's what that previous slide was talking about. No, that's where that one came into play. I thought it was part of the conceptual insight. It wasn't. Yeah.
I just wanted, I had an answer for you.
Okay, great. Yeah.
It's an OSHA regulation. Dr. Pruitt said that notice is on all the biology labs now at Birmingham. He said it shouldn't prevent classes being held there.
Okay. So there really wasn't a spill or anything. It's just
right. It seems to be just a standard.
Okay.
Warning.
Is that why they're locked though?
I don't know. Are they usually unlocked?
They're usually unlocked. Yeah.
Okay. I put that in my email. He didn't respond to that part of it.
Okay. Well, at some point today, I bet you there's going to be a biology class and say, "Why is the lab locked?" And yeah, hopefully someone will unlock it then. Yeah. You have a master?
I don't.
Oh, you don't.
I've talked to security and they said that they will, respond to. They came up and looked at it. Yeah. They didn't know anything about it. They said they would open them up.
Okay.
Happily.
Okay. They usually open when they open the classes, but since they were locked and the class was unlocked and they had signs on the door, I just jumped.
It all added to it. Yeah.
Okay. All right. Thank you so much.
Thank
really
you.
Appreciate it.
Absolutely. I'll send you copies on these.
Okay. Thank you. All right. So, still don't know why the door's locked. The signs are because they have biology stuff in there.
That's kind of weird to already have them up, like, all the time, whereas...
Well, they've been up before, but you see the doors have always been open, so you wouldn't see them.
Exactly.
So that still doesn't answer my question, why are the doors locked today?
Right.
So I assumed it was because of the sign, but it's not. So why are they locked today? So my assumption was very faulty. Okay. Now, so far I take it's been a lot of blah, 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 right? Let's see if we can come up with this here. If a function f is differentiable, that means you can take its derivative at the point x equals c. That guarantees, that implies it has to be true that f is continuous at c. Because if it wasn't continuous, how in the world could it be differentiable there? Okay? It couldn't. And that's what that last slide was indicating. Okay? Now, do not do this. Do not assume that if a function is continuous at c, it's also differentiable at c. This doesn't go both ways. It only points in one direction. If f is differentiable, you know it's differentiable, you know the function is continuous at that point. It may not be continuous at a point very close by, but at c, it's got to be continuous. Now, why is it true, not necessarily true, that f is continuous at c? If that's true, it would guarantee it to be differentiable. I'm going to introduce a concept that the book doesn't really use yet. Maybe they're going to get to it later. If f is differentiable, that implies that it's, and this is not a very well-defined term, smooth. Because if it has a derivative, that means there is some tangent point, a tangent line you can draw at that point, and it's going to work. Okay? Now, continuity doesn't guarantee that. What if we had a line that went like this and then like this? It's smooth up to here, but not smooth there. What is the tangent lines there, that's continuous there, but sure the slopes are not continuous. So therefore it wouldn't be differentiable even though it's continuous. But if it's differentiable, it's got to be continuous. That's the main point. Okay? Now, they go through a proof of this, and the slideshow doesn't pursue any of it. For those of you who are math majors, which I think is only one, I would definitely go through the proof. Make sure you understand the steps. If you don't, ask me and we can go over those. But since they don't show it in the slides, let's move on to example 9, which, by the way, is also not in the slides. But we'll do example 9 here. Here's example 9. Let's see if we can get. We'll do it here. Okay. Here's a function. F of x is equal to absolute value x. Okay. Do you think that's a continuous function or not? Yes, it is. Okay? Continuous everywhere, including x equals 0. How does this function look? It's a v. It's your identity function this way and the opposite of the identity function this way. It's f of x equal x anytime x is positive, and f of x equal minus x anytime x is negative, right? And at 0, it's 0. So that's a nice continuous function. Does that mean it's a differentiable function? Everywhere. Okay? What is the derivative anywhere here?
Oh, I guess you couldn't.
It's a minus 1.
Oh, yeah, okay.
Isn't the slope minus 1 there?
Okay.
Anywhere here, what's the slope? Positive 1. Even right down here, it's positive 1. Even right there, it's positive 1. Even right here, it's minus 1. But at 0, what is it? It's not defined. Because the limit, as you approach 0 from either side of the slope, is minus 1 here, plus 1 here, undefined at 0. So just because it's continuous doesn't mean it's differentiable. But if it's differentiable, and it's differentiable here and it's differentiable there, not differentiable at x equals 0, but at any place it is differentiable, it's also guaranteed to be continuous there. But if it's not differentiable, doesn't mean it's not continuous. If it is differentiable, it's got to be continuous. That's all this one says. So this just is illustrating this goes one way, it doesn't go the other way. The fact it's continuous does not guarantee differentiability, but the fact it's differentiable does guarantee continuity. Okay. Now, another graphical insight. And they give you these graphical insights. Well, no, the last one was conceptual insight, but they didn't give you much to do with it except describing it. Here's a graphical insight that we are going to use. Differentiability has an important graphical interpretation in terms of what they call local linearity. We say the f is locally linear at x equal a if the graph looks more and more like a straight line as we zoom closer and closer to that point, a, f of a. Okay? Meaning it resembles a line. It looks like it's locally linear there. Okay? And here's the illustration of that. Oh, we can get it all on one slide. Maybe at first I couldn't, but let's try it. Okay. Did I just do that? Put them over here. It's much more solid thing. That's just a little bitty thing. Okay. Here's a function. I don't know what function that is. It's just some function. Okay? Now that function, at this point right here, is that locally linear? Well, it's certainly changing, but is it locally linear? Well, let's zoom in on just that little rectangle. let's do that. And at that little rectangle, if you take that and blow it up here to the whole thing here, you see you've got this, okay? Everything in this rectangle is now here. Let's zoom in a little closer, like here. Zoom in on that, and that gets here. Zoom in here, and you can hardly tell the points apart. Get close enough, get small enough domain, and they appear to be the same function. The tangent line and the line, okay, the curve. If that's the case, this is said to be locally linear. If you get the neighborhood to be small enough, it looks like there's a straight line. It certainly isn't a straight line here, nor here, nor here, but here and that, I can't tell a difference. And they are on top of each other. Which means, do this here, and they look like they're on top of each other too almost. So that's what it means locally linear. You know the other word for that? Smooth. Okay? Meaning that there's no jagged change of direction. No angles, no cusps, nothing else that would keep it from being smooth. And if it's smooth, then it's locally linear is a little easier to define. Smooth isn't. Okay? But if it looks smooth, you've got a good chance it's locally linear. Okay. Now, if we go back to the previous example and try to get locally linear on it, here is our absolute value function that we just did. Well, I got it whether I want it or not. So, let's zoom in on the absolute value function here. Let's look at just that little portion there. Zoom in on that, and you get this. Well, let's zoom again. Zoom in on that, and you get this. You can zoom till the cows come home, and it's always going to have that point there, that angle there. There's no way you're ever going to get rid of it. So this is not locally linear at x equals 0. It is at x equal 0.1, 0.2, 0.01, 1, any value there is locally linear. You could just focus on just that little portion, like just the portion. If you're at this point, just here, and here, and here, and soon all you see is a straight line because you lose the other side. You're getting so small. Then it's locally linear at any point, but at 0, no matter how many times you zoom, is still going to have that angle there, okay? Not going to be ever straightened out, okay? Now, that's one problem with tangent lines. If the tangent line is, if the slope of the tangent line or the first derivative is not continuous at a point, you're not going to be differentiable at that point, okay? But we have another problem, Houston, and here's what it might be. Show that the function f of x equal x to the 1/3 is not differentiable at x equals 0. So here's the function f of x equal x to the 1/3. Show it's not differentiable at x equals 0. Well, how are you going to show that it's not differentiable? Take a derivative. Very good. Like Jesus, right? Okay. F prime of x is going to be what? 1/3 x to the negative. Negative 2/3. Very good. Which is the same as 1/3. That 3's down there. The x to the 2/3 goes down there, right? Okay, which is 1 over 3 times the, let's see, how do I do it? The cube root of x squared, right? Okay. So f prime at 0 is what? 1 over 3 times the cube root of 0 squared. What's the cube root of 0?
Is that undefined?
It's 0.
It's 0, okay.
In the denominator, it becomes undefined. Okay, but the cube root of 0 is 0. This is 1 over 0. And guess what that is? That is undefined. So, sure enough, the tangent line, even though, and here's the problem with my thing, even though that's a smooth curve and locally linear there, guess what? Still the derivative is undefined. The tangent line to the graph at the origin has a vertical, is the vertical of the y-axis, and the derivative of L prime does not exist. So therefore, even though it's a smooth function, even though it's a continuous function, even though it's a locally linear function, if that derivative is undefined, then the derivative doesn't exist at that point. Okay? So again, if it's differentiable, that guarantees continuity, but none of these other things do. Continuity doesn't imply differentiability. Local linearity doesn't imply differentiability. Smoothness doesn't imply local linearity. You also must not have a vertical tangent line, because the vertical tangent line does not have a value. Okay? Now, they did it with the limit, but we had already done our integration rule, derivative rules, so why go through the limits when we can use the rules? Okay. As a final remark here, then, we mentioned there are more complicated ways in which a continuous function can fail to be differentiable. Okay? We've seen a continuous function is not differentiable at a point where the continuity, at the point where there's an angle, a cusp, or a vertical tangent line. Okay? There are other problems you can encounter. And they love these kind of problems. They have them over and over again. Okay? They are a function that's a continuous function. The graph of f of x equal x sine 1 over x. We've hit this so many times before. I get a little tired of it, okay? But this function, if you were to graph it, it is never defined at x equals 0. So that's one problem. The function's not defined there. It does have it doesn't even have a limit there. Because as you get closer and closer to x equals 0, it's still going up and down, faster and faster and faster, but it's still not ever reaching a limit. If you did the secant lines, there is no limiting position. They just keep going back and forth and back and forth and back and forth between those without ever coming to a limit. So, and in my mind, why worry about all those consequences? You look at the innermost function here. If that's not defined, there's no way you can take the sign of an undefined value. Because 1 over x is not defined. You can't do it. So why take a sign of something you can't even determine what the value is? Okay? Don't try. Okay? It just is a waste of time. Okay? That, I think, is the last slide. So let's go to the exercises. All right. First one, preliminary question. What is the slope of the tangent line through the point 2, f of 2, if f, okay, so we want this, what we're looking for is slope of the tangent line. If, here's the conditions. Oh, through the point. Sorry, let me get that first. Through the point to f of 2, okay, not much detail there, if f prime of x is equal to x cubed. What is the slope of the tangent line through the point to f of 2? And that's all we know is f of 2, okay? If f prime of x is equal to x cubed. Now, notice what they didn't ask. They did not ask for the equation of the tangent line. All they're asking for is the slope of the tangent line.
Well, wouldn't all we have to do is just plug it in because we already have the derivative?
That is exactly it. The slope of the tangent line would be f prime at x equal 2, and that would be 2 to the third is 8. That's your slope of the tangent line. Okay, that's it. That's all that there was to it. They wanted you to think through and figure that out. Okay, does everybody see that? Very good. Now, if they asked for the equation of the tangent line, you would have this expression in there somewhere, okay? And you wouldn't have total information. Okay, let's do number 2. Evaluate f minus g prime at 1 and 3f plus 2g prime at 1, assuming that f prime of 1 is equal to 3 and g prime of 1 is equal to 5. Given that, given those last two pieces of information, can you get what f minus g prime of 1 is?
You just plug it in? Just plug in f prime of 1, or
Okay, you got to do one little thing first. What is that defined as?
Oh, okay. G prime, gotcha.
Yeah, the difference of two functions, the derivative of the difference of two function is the derivative of a difference function is the difference of the derivatives. Okay, and plugging in the 1 there, then we can get what? 3 minus 5 equal negative 2. Okay, so this is negative 2. How about that one?
Same thing. So it would be 9 plus 10.
Okay, so this would be 3 times 3, which is 9, plus 2 times 5, which is 10. So that sure enough would be 19. All right. Yeah. Make sense? Just getting you to use your sum and difference of derivatives formula. Negative 2 and 19. Got it. Okay. Number 3. To which of the following does the power rule apply? Okay, here's the A. F of x is equal to x squared. Okay, and the other B is f of x is equal to 2 to the e. To which of those two does the power rule apply? Would you use the power rule on A?
Yes.
Yes, you would. F prime would be what?
2x to the 1. Just 2x.
2x. Got it. Would you use the power rule on B? Why not? Is what? Okay. Does anyone know what f prime of x would be?
Would it still be 2e? Or no? 2e.
Okay.
2e minus 1.
Okay. Not quite. You're using a power rule there. Say again? What is E?
What's it, 3? No.
It's an irrational number near 2.7.
2.
Right.
Yeah.
A number. A number. Okay? So 2 raised to a number is a number. And the derivative of the number is?
0.
0. You didn't need the power rule for that. Right. Make sense? Okay. All they are going to say is A back here because it's which one would it be? And sure enough, it's. Oh, I didn't see the rest of them. I just saw A and B. Let's do C. Okay. All right. F of x equal x to the e. Would you use the power rule there?
Would that still be the same case with it being 0?
Okay, except x is
Or
not
is
a.
it just x?
No. Do what you were trying to do before.
So 0.
No.
X to the negative, x to the, let's see, e minus 1?
Okay. I thought you were leaving it out before. E x to the e minus 1. Yeah. E is a number, something close to 2.7, times x to the something close to 1.7. Okay? Yes, you did use the power rule for doing that. Yeah. So you would use it there. So you used it on A and you used it on C. Let's see what D is. F of x equal e to the x. What's your f prime?
Still, yeah.
E to the x, yeah. You don't use the power rule there. That's an exponential function. So this is not the power rule, and that's not the power rule. You use other rules for those. Okay, how about E? E is f of x equal x to the x. Oh. Okay, what do we do with that one?
Would be
The answer is not the power rule.
Yeah.
That's all we can answer here. There is a way to do the first derivative of that. We haven't gotten there yet. And one of you was hinting at it, and I think you have a really good idea. If you were to take a log of that function first, then you can take a derivative, okay, and then go backwards. But right now, not the power rule. You can take it, but not the power rule. F, is this the last one? Yeah, good, because we're running out of room. F of x is equal to x to the minus 4/5. Yes, you use the power rule there, and what does that give you? F prime. The book is asking for this. I'm asking for it to give you practice. Negative 4/5
to the negative 9/5.
Negative 9/5. You're absolutely right. Now, is that defined everywhere? Where is it not defined?
Negative, would be 0.
X equals 0, not defined, because not one of the function is even defined there. Okay? So yeah, that's everywhere it's defined, that would be its derivative. So basically we had A, C, and E, and F. A, C, and F. Okay? Let's see what the book got. Oh. Huh. They said B was. I don't believe them. Okay?
What was their explanation for?
They don't give a thing. Oh, wait. No. They say B was, and it's not. A, C, and F. B is 0. Okay, thank you. Never mind. Okay. I'll have to deal with that later. All right, let's do number 4. I think I'm going to have to clear some room. If you were trying to use the power rule before on B, F prime, just like you were trying to do, let's go on and carry that out. 2 to the E. What you were trying to say was E 2 to the E minus 1. If you were trying to use the power rule, you would get that. Okay? Someone with a calculator, I'd like you to plug that in and tell me what you would get. You got the E key, E to the 1 times 2, then do your caret key for the exponent, and then do E to the 1 minus 1 in parentheses and hit equal. It may actually give you a number, but I'm curious of what number it would give you.
This is saying the decimal approximation is 8.944.
Wow. Yeah, that's probably not far from true. Because E is, if E is 2.7, I mean, 2.7, yeah, 2.7, I want to make sure it's right. Then E minus 1 would be 1.7, so that would be almost 2, so 2 squared would be 4, so it would be something a little bit less than 4. Let's just call it 3, not that it's exactly 3. And 3 times 2 would be 2.7, would be something close to 6, 7, 8, something in there, yeah. But still, that's wrong. 2 to the E is a number, okay? And when you take the derivative of the number, you should get 0. So, sorry about that, folks. I think they're wrong, okay, in the back. But let's go on to erase all those and do number 4. Choose A or B. Derivative does not exist if the tangent line is A, horizontal, or B, vertical. The derivative does not exist if the tangent line is horizontal or vertical. Which is the case? It's true. The derivative does not exist if the tangent line is horizontal or if the tangent line is vertical. Vertical, exactly. So that would be B. They better have that one right. Okay. Yes, they got it right. And number 5. Which property distinguishes f of x equal e to the x from all other exponential functions, g of x equal b to the x? F of x equal e to the x and g of x equal b to the x. Okay. What property distinguishes f from g? Yeah, the derivative of e to the x is e to the x. Derivative of g to the x is some constant times b to the x. In fact, that constant is log b. Okay? So, this is the thing. F prime of x is equal to e to the x, where g prime of x is equal to log b times b to the x. Okay. There is a coefficient for g prime that is not for f. Okay. Let's see just how they answered that in the back. The line tangent to f of x equals g of x equals 0 has a slope equal to 1. Okay, that's true too. Okay. All right. Homework exercises then. Do any of the odds 1 through 5, any of the odds 7 through 13. Do either 15 or 17 or both if you choose. Do 19. Do any of the odds 21 to 31. Do any of the odds either 33 or 35 or both, depending on which you prefer. Any of the odds 37 to 41. And then I would say do any of the odds 43 through, there's a whole bunch here. $69. But I wouldn't just do 1 or 2 of them. I'd do a few in each sort of group of those. Then do any of the odds 71 to 75, and then do any of the odds 77 through 81. Then do either 85 or 87 or both, and try to look at 89 and 91. You don't have to actually do those, but look at them. And then I was going to say you can look at further insights and challenges. I'm not sure there's anything there that might be worth a paper topic, but if you see something that just turns you on, go for it. So we'll start next time with product and quotient rules, okay? And we will go from there. That's 3.3.